Welcome to Talk Tensors. Today we're doing something a little different. We are staring directly into the future of generative media, but we aren't talking about static images anymore. We're kind of past that. Today, we're dissecting the massive engineering leap required to go from generating a frozen moment in time to, well, high-fidelity, temporally consistent video.
It's the difference between a photograph and a hallucination that actually obeys the laws of physics, or at least tries to.
And that's the hook for this deep dive, right? I think a lot of us have gotten desensitized. We're used to typing astronaut riding a horse on Mars and getting a perfect image in, 3 seconds?
Mm-hmm.
But making a video of that same scene where the horse actually gallops, the dust settles, and the astronaut doesn't just morph into a centaur halfway through.
That's an exponentially harder problem. It's not just about adding a time axis, it's about world modeling. If you generate a video, you aren't just, painting pixels. You have to simulate continuity. You have to understand object permanence.
An object can't just dissolve and reappear as a toaster. Which brings us right to the core problem we're unpacking today, the temporal dimension. There's this classic analogy in the field involving a cat walking across a garden.
Right. In a static image, the cat is just data, a collection of pixels that semantically mean cat.
Mm-hmm.
But in a video, as that cat steps forward, its pose has to change, the light on its fur shifts, the background is revealed behind it. But, and this is the engineering bottleneck, it has to remain the same cat.
And the garden can't suddenly turn into a desert because the camera moved 2 degrees.
Precisely. And historically, before the architectures we're discussing, you had 3 bad options.
Okay.
1, frame-by-frame generation. That gives you that awful flickering effect. The model has 0 memory.
Right. 2,
generate all the frames at once. That just completely destroys your GPU memory. Video data is massive.
A volumetric cube of data.
And 3 was these early hybrid attempts that were just low-quality, blurry messes.
So let's get into the architecture that actually started to solve this. We have to start with the foundation. Latent diffusion models, or LDMs. Now, most of our listeners will know diffusion, but walk us through why latent diffusion specifically was the prerequisite for all of this.
It all comes down to the curse of dimensionality. If you try to run a diffusion process on raw pixels, say a 4K video, you are calculating noise removal for millions and millions of values.
It's computationally impossible.
For anything but a supercomputer, yeah. So LDMs change the game with something called perceptual compression.
Let's double-click on that distinction, perceptual versus semantic.
Think of it this way. An image has a ton of high-frequency detail, the exact color of a pixel in a shadow, the digital noise in the sky.
Perceptual data.
Right. Your eye sees it, but it doesn't carry much meaning. The semantic data is the concept. There's a cat, it's orange, it's walking.
So the model needs to ignore the noise and focus on the catness.
Exactly. An LDM uses an autoencoder to compress the image into a latent space. It strips away all that imperceptible detail, but keeps the semantic structure.
It's like turning a WAV file into an MP3, but for visual concepts.
That's a great analogy. You train the autoencoder once to get into this really efficient space. Then all the heavy lifting, the diffusion, the denoising, it all happens in that smaller latent space. It makes the math tractable.
But that's standard for images now, like with stable diffusion. The breakthrough for video is how we inject time into that static map. A latent space is a map of concepts, not a timeline.
And this is where the align your latents approach comes in. It's brilliant in its modularity. The engineers realize, look, we don't need to throw away the image models we've spent millions of dollars on. We can just plug in time.
So they take a standard image model and physically insert new layers, like an expansion pack.
In a sense, yeah. They insert temporal layers into the neural network architecture. Imagine the network is a stack of pancakes processing an image. They just slide new layers, temporal attention and 3D convolutions between the existing ones.
Okay, so the existing spatial layers are looking at the cat shape to make sure it looks like a cat. What are the new temporal layers looking at?
They look across the frames. So the spatial layers make sure each individual frame has high fidelity. The temporal layers look at the latent for frame 1, frame 2, frame 3, and so on. They compute attention scores across that timeline to basically say, hey, align these. Make sure the pixels flow logically from A to B to C.
And because it's so modular, this is what allows for things like Dream Booth integration in video, right? That was a big deal.
Oh, it's huge. Dream Booth is a technique where you fine-tune the image backbone on a specific object, say your pet dog or that Skilla's teapot token they use for testing.
Right.
Because the temporal layers are just looking for motion consistency, you can train the image part on your specific teapot, and the temporal layers automatically know how to animate it. even if they've never seen that specific teapot move before.
That is wild. It decouples what it is from how it moves.
To an extent, yes.
Yeah.
It generalizes the motion dynamics.
But there's still a problem with complex narratives. We talked about one cat. What if the prompt is a man walking with a black dog on his right while a blue car drives from the opposite direction?
The compositional understanding bottleneck.
Standard models just blend that into a soup. You get a blue dog.
Exactly. They're basically bag of words models. They struggle with structured relationships. This is where a framework called MoV AI comes in.
MoV AI, multimodal original video AI. What are they doing differently under the hood?
They treat video generation not as a pixel problem, but as a scene parsing problem. They use a compositional scene parser, or CSP.
So before it even generates a single pixel, it builds a plan.
Precisely. It decomposes the prompt into a hierarchical scene graph. It diagrams the sentence. It finds the entities man, dog, car. It figures out their relationships. Dog is right of man. And crucially, it parses the temporal annotations. It understands the choreography before it paints.
It's like building a screenplay. But how does it force the pixels to obey that plan? It's one thing to know the dog should be there, another to actually put it there.
They use a temporal spatial attention mechanism, or TSM.
TSM.
In other models, you might have spatial attention and temporal attention happening separately. TSM unifies them. It creates an attention map that looks at relationships within the frame and across frames simultaneously.
So it's locking that relationship in 4D space.
Correct. And they don't try to do it all at once. That's the third innovation. Progressive video refinement, or PVR. They generate a coarse, low frame rate version first to get the basic motion right, and then they iteratively upscale and refine it.
That makes sense. Much more stable than trying to hallucinate 4K from pure noise.
And the metrics back it up. They use FED Freshit video distance.
Right, we see that acronym everywhere. What's it actually measuring?
FED is the standard for quality. It basically measures the statistical distance between a fake video and a real one. Lower is better. MoV AI dropped the FED score significantly compared to older models.
Meaning the videos just look more natural.
Statistically indistinguishable from real footage, yeah.
Okay, let's pivot to control. Because text isn't always enough. If I'm an animator, I might have a sketch or a specific human pose I need to match.
And this is where ControlNet enters the chat. And ControlNet is structurally just one of the most elegant architectures in this whole field.
It solves the problem of how do I guide a massive model without breaking it?
Yes, exactly. The problem with just fine-tuning a huge model is you get catastrophic forgetting. It forgets how to draw a car because you forced it to learn your sketch style.
So ControlNet locks the original model, puts it in a glass box.
Correct. It freezes the weights of the production-ready backbone. Then it creates a trainable copy of just the encoding layers.
So you have two parallel streams, the giant frozen brain and the smaller flexible student.
Exactly. But the magic is how they connect them. They use zero convolutions.
A zero convolution, it sounds like it does nothing.
And that's the point. It's a one-by-one convolution layer where the weights and biases are initialized to exactly zero.
Why zero?
Because mathematically, if the weights are zero, the output of the ControlNet block is zero. Which means at the start of training, the result is simply original model output plus zero.
So the model behaves exactly like the original.
It's a safe starting line. You can start training without introducing any harmful noise that would just scramble the whole process.
You're not throwing a wrench in the engine, you're just gently placing a gear that isn't spinning yet.
Perfect analogy. And as training progresses, those zero weights slowly shift, and the control signal, the sketch, the pose, gently starts to influence the generation.
And this leads to that really bizarre observation they made, the sudden convergence phenomenon.
I love this detail. You watch the training loss, and for thousands and thousands of steps, nothing. The model is ignoring your control signal.
Just generating normal images.
And then all of a sudden, almost instantly, the model just snaps into place.
Right.
It suddenly understands how to map the canny edge or the human pose to the image.
It's not linear learning. It's a phase transition.
It is. It's like learning to ride a bike. You fall, you fall, you fall, and then click, you're riding.
Okay, so we have structure, consistency, and control. But the elephant in the room with diffusion is always speed. It's painfully slow.
It is. A standard diffusion process can take hundreds of denoising steps to get a clean frame. You multiply that by 24 frames per second.
And you're waiting for hours. Which brings us to Nvidia FastGen and this idea of distillation.
Distillation is the art of teaching a small, fast student model to mimic a big, slow teacher model. The goal is to compress those hundreds of steps into just 1 or maybe 4 steps.
We're talking 10x to 100x speedups. That's the difference between rendering overnight and rendering in real time.
Right. There are a couple of ways to do it. Trajectory-based, where you force the student to copy the teacher's exact path. Or distribution-based, where you just say, I don't care how you get there, just make your final output look the same.
But to understand why this works, we need to touch on the math underneath. The SDEs, stochastic differential equations.
I'll keep this painless, I promise. But yes, diffusion models are fundamentally just solving SDEs. Imagine your video. We add noise to it over time until it's pure static. That's the forward SDE.
Increasing entropy.
The generative process is the reverse SDE. We're mathematically reversing time, turning static back into data. And there are 2 main flavors of this, VE and VP.
Variance exploding and variance preserving.
Right. Variance exploding, or VE, is where as you add noise, the variance just keeps getting bigger and bigger. It explodes. Older models use this.
And VP.
Variance preserving. This is what modern models use. As you add noise, you also scale down the original data, so the total energy stays bounded. It's mathematically cleaner, and neural nets love it because it keeps the numbers stable.
And how do we actually solve these equations?
We use numerical solvers. But the cool trick is the predictor-corrector sampler.
Sounds like a buddy cop movie.
It kind of is.
Yeah.
You have the predictor, which takes a guess at the next step in the denoising process. It moves you from very noisy to slightly less noisy, but it makes little errors.
So the corrector steps in to clean up.
Yes. The corrector uses something like Langevin dynamics to take the predictor's guess and just kind of scrub it. It smooths out the errors before you move to the next step.
So it's step Polish.
Exactly. It improves sample quality a lot.
Before we get to our speculative segment, I want to touch on one more architecture, Cog Video X. They're doing something interesting with the VAE.
Cog Video X is pushing the envelope on compression. We talked about 2D VAEs for images. Cog Video X uses a 3D variational autoencoder.
3B meaning time is the third dimension.
Yes. Instead of compressing each frame individually, it compresses a whole block of video frames together. It compresses along the spatial axis and the temporal axis.
Which is key because so much video data is redundant. If I'm filming a talking head, the background doesn't change for 5 frames.
Exactly. Why compress that background 5 separate times? A 3D VAE squashes that redundancy down, making the latent space richer and way more efficient.
And they also have this expert transformer thing, the expert adaptive layer norm.
It's a mechanism to fuse the text prompt deeper into the model. Sometimes a model will just ignore the text if the visuals get too complex. This forces the model to adapt its internal layers based on the specific text.
It enforces the prompt's authority over the physics engine?
That's a great way to put it.
Okay, we've covered the stack. Latents, temporal layers, scene graphs, control nets, SDEs. Now it's time for novel notions.
All right, and the disclaimer, these are speculative ideas based on the text trajectory. Do not go build a startup on these.
Oh, do, but don't blame us if it hallucinates. I'll start. I'm looking at that causal distillation stuff from FastGen, and I'm thinking about video games, but not rendering polygons, a blockwise autoregressive world model.
Okay, explain that.
Imagine a game engine with no 3D assets, no polygons, no textures. It's just a massive video diffusion model. You hold a controller, the model takes the last minute of gameplay video as its history, and your controller input as a condition.
And it generates the next 3 seconds of video in real time.
Yes. It generates the reality of the game on the fly. You push left, it hallucinates what's to the left, keeping it consistent with the history buffer. It's an infinite, non-repeating world.
That's the world simulator concept people are talking about.
Yeah.
If the temporal consistency is high enough, the physics would just emerge naturally.
Exactly. The game is just a prediction of what happens next.
Okay, my turn. My notion takes that spatiotemporal compositional diffusion idea and applies it to editing. Let's call it logic flow editing.
Go on.
Right now, video editing is just cutting clips. It's mechanical. Imagine an editor where you don't touch the timeline. You touch the logic. You have a slider for wind direction. You have another slider for sadness.
Sadness.
Yes. You drag the slider, and the model rewrites the physics of the scene. The rain changes angle, the lighting drops, the character's posture slumps. You're not re-rendering from scratch. You're using the attention maps to shift the relationships of the objects instantly.
That changes filmmaking from capturing something to sculpting it.
Precisely. You get control over the latent concepts of the scene, not just the color grade.
What a time to be alive. Okay, let's wrap this up. We've gone deep today.
We have. We started with the efficiency of latent diffusion. Don't process pixels, process meaning. Then we saw how align your latents injects time to solve the flickering problem.
We looked at MoV AI solving the cat-dog car problem with scene graphs, and ControlNet solving guidance with those clever zero convolutions.
And we touched on the heavy math of SDEs and how distillation is finally making this stuff fast enough to matter in the real world.
For me, the big takeaway is we're moving past the, wow, it made a video phase.
I think so too. We are entering the phase of compositional understanding. The models aren't just predicting the next pixel's color anymore. They're beginning to understand scene graphs, that objects have permanence, relationships, physics. The next big leap isn't resolution, it's logic.
And when logic meets creativity, that's when things get really interesting. Thank you for diving in with us.
Until next time, keep optimizing your gradients.